Welcome, everyone, to this week's Zoom for Thought. We've got Junekey this week finally talking to us about some analysis in the form of point-free measure theory. Take it away.
Yeah, I'm afraid it's a bit about algebra, actually. Anyway, okay, so hello, everyone. I'm Junekey, and today I'm going to talk about point-free measure theory, which is an approach to measure theory in a more abstract viewpoint. And specifically, it forgets the notion of points and tries to recover and possibly extend the whole measure theory only with the notion of measurable sets. So the reason for doing that is somewhat related to the following famous quote, often thought to be due to Grothendieck, which is, it is better to have a good category with bad objects than to have a bad category with good objects. So the goal here is, I guess, to allow more variety of ways of constructing measure spaces, which might simplify some aspects of the theory, even though we are actually generalizing the theory. So yeah, the motivation for me personally of studying this topic was so-called conditional probability measure. I guess anyone who studied the modern measure theoretic probability theory should know how we define conditional expectation, right? Yeah, it's defined to be some Radon-Nikodym derivative, and the reason why we define it that way is that the more elementary notion of conditional probability distribution is somewhat flawed in many ways. So we try very hard to avoid mentioning conditional distribution when we define conditional expectation. However, we sometimes do need the raw notion of conditional distribution, and often the notion of conditional expectation alone is not so sufficient. This actually happened to me back in 2014. So I Googled and found out that it is in fact possible to define a good enough notion conditional probability measure under some technical condition. So I applied that theory into my problem at the time, and I just moved on. But I was, in fact, not so happy about that. The specific condition that was needed was that the probability space we're working on must be standard Borel. I'll not talk about what standard Borel means, but roughly speaking, the problem of finding the conditional probability measure is to find a Radon-Nikodym derivative, but this time it's a measure-valued measure. Yeah, so being standard Borel somehow enables us to reduce the number of components into a manageable size, let's say being countable, so that we can obtain the Radon-Nikodym derivative in a component-wise manner, and then gather them together. So the reason why having countably many components matters here is that it's roughly because Radon-Nikodym derivative is not unique. I mean, we often pretend it is unique, but it's not. I mean, it's only unique up to almost everywhere equivalence, right? So that prevents us from collecting uncountably many Radon-Nikodym derivatives into something sane. So yeah, at the time, I was not so happy about the theory of standard Borel. Yeah, because I think standard Borelness is not really very stable property. It's way too easily broken. So, and accidentally, point-free measure theory caught my eyes, and I thought it must be the right alternative. Yeah, it eventually turned out that it does not really significantly improve anything, but I think the point-free viewpoint helped me a lot in many ways and gave me lots of valuable insights. Yeah, by the way, point-free measure theory is not a standard terminology. It seems that nobody collectively calls this attitude toward measure theory into a single term. I don't know why. So I just came up with some words. I mean, yeah. I actually first coined the term pointless measure theory. But yeah, because it seems like pointless topology is a standard terminology. But yeah, it's silly, right? I mean, Why does anyone ever want to study a pointless theory? It's
Well,
really...
topology is okay. Everyone accepts that it's pointless, but measure
Okay.
theory.
Yeah. Anyway, that's why I changed it into point-free measure theory. Anyway, so let me stop rambling and get into real math. So let's briefly review the conventional pointed measure theory. I'm sorry about that. So in pointed measure theory, we study measure space, which consists of a set of points and a sigma algebra on that, whose elements are called measurable sets, and we define a measure on that. And on top of that, we study things like measurable functions, LP spaces, things like convergence theorems. Also, we study things like various relationship between modes of convergences. Yeah, something like that. Yeah, and comparing these to general topology, say, which I think has many things in common with measure theory. There are some peculiar aspects of measure theory, and one of them is the role of points. I mean, for example, knowing the value of a measurable function at a specific point means nothing. It has literally zero information because we usually factor things out by almost everywhere equivalence, right? So yeah, as a whole, pointwise behavior do matter, but as individuals, they are nothing. So this is in contrast to the situation for, let's say, continuous functions, because in that case, pointwise values do give us meaningful information, right? So in pointed measure theory, ironically, pointwise behavior is pointless. So yeah, that's one of the peculiar aspect of the measure theory. And yeah, also the role of countability in measure theory is so prominent, so that, for example, any convergence theorems are hardly ever true for nets. And here is another monster that is called pointwise almost everywhere convergence. And yeah, I really don't like this notion because it's not a topological convergence, meaning that it's not coming from a topology. Yeah, so anyway, the point-free approach that I want to explain fixes these problems in some sense by developing theory only with the notion of measurable sets without the notion of points. Yeah, so let's get into point-free measure theory from now on. So the abstraction of the concept of the algebra of measurable sets, it's so-called Boolean rings. So a Boolean ring is a ring, algebraic ring, let's say with unity, such that every element squares to itself. So a prototypical example of Boolean rings is the power set of any set. So one can easily verify that by viewing this symmetric difference as the addition and this intersection as the multiplication, you can show that this triple actually forms a ring, where the additive identity is the empty set and the multiplicative identity is the whole set X. More generally, any set algebra is a Boolean ring in the same way. So in particular, sigma algebra of measurable sets is a Boolean ring. In fact, every Boolean ring is a form of set algebra, and we'll get into that later. So once we define the abstract notion of measurable sets, so we can define the notion of measures. So a measure is any function on a Boolean ring that sends 0 to 0, and it distributes the addition for disjoint elements. And here, by disjoint, I mean the product is 0. I mean, it makes sense because the product is meant to be the intersection, as you can see here. So yeah, and then we call this pair a measured ring, and yeah, this is the object we want to study. So here are some remarks. Yeah, first we can replace this interval by something else. Let's say a commutative monoid, for example, and these axioms still do make sense. And in particular, I'm interested in the case when this is replaced by some locally convex space. But the correct way of doing that is not simple to explain. So I will not get into that. And second, we do not require our measure to be countably additive. The reason will be explained later. For now, just remember that this second axiom is the abstraction of finite additivity rather than countable additivity. So here are some simple facts about Boolean rings. So the first one is that every element is the additive inverse of itself. This follows just by squaring a plus a, which gives you 2a equals 4a. Therefore, 2a is 0. And second, every Boolean ring must be commutative. Yeah, you can just check it by squaring a plus b, which gives you ab equals minus ba equals ba because of the first part. And third one is that the only Boolean ring having no zero divisor is the field of two elements. This follows because if you compute a times 1 plus a, you always get 0. So one of these two must be 0, which implies that a is either 0 or 1. And the trivial consequence of this is that every prime ideal is maximal. Yeah, this follows. So if you choose any prime ideal and compute the quotient ring, then this is a Boolean ring without any zero divisors, so it must be F2, which is a field. Therefore, the kernel must be maximal. So yeah, that's that. And so we can view Boolean rings in the ring theoretic perspectives, but also we can view them in the order theoretic perspectives. Because they admit a very natural partial ordering. Specifically, we say an element A is less than or equal to B if and only if their product is exactly A, which makes sense because, again, A times B is supposed to be the intersection. So intersection is A precisely when A is a subset of B. So yeah, this relation is really an abstraction of the subset relation. So given this partial ordering, our ring B becomes a distributive lattice with this notion of infimum or meet. Yeah, meet is just the product. And here the supremum or join is given as this formula. And you can see that A plus B is meant to be symmetric difference. And you're adding back what's missing. So what you get is the union. I hope this makes sense for you. And and with these formulas for the intersection and the union, you can recover all of the reasonable set theoretic identities as long as there are finitely many terms involved. Yeah, and also the notion of ring theoretic ideals is equivalent to the notion of order theoretic ideals. And I suppose everyone is very familiar with this one. So let me explain what this means. So an order theoretic ideal is a subset of a Boolean ring such that it is closed under finite joins. So whenever you choose two elements, their join is inside the ideal. And it's closed downward, which means that whenever you have an element inside the ideal, every element that is below that element must belong to the same ideal as well. So you might see that this first condition is roughly corresponding to closure under addition in this side, and the second condition is roughly corresponding to the closure under the multiplication by any elements in the ring. Yeah, it's roughly the reason why these two notions are the same. Finally, we say a Boolean ring complete if every subset admits the supremum. So for example, power set algebra is a complete Boolean ring because whenever you have a collection of subsets, just take the union, then that union must be the supremum of the collection. But in contrast to that, Borel sigma algebras and Lubeck sigma algebras on, say, unit interval, they are not complete. And the reason is basically because there are non-measurable sets. And yeah, but they're sigma complete, which means that even though every subset might not have supremum, but every countable subset should admit the supremum. That's what we mean by sigma complete. And it's pretty much just the definition of sigma algebra. So every sigma algebra is sigma complete by definition, but they are actually rarely complete. So completeness is a really strictly stronger condition than sigma completeness. Okay, so since pure algebra is dull, let's give some topology so that we can talk about convergence. Right, so we first introduced this notation for set of elements of finite measure. And for each element of finite measure, we define a pseudometric. Like this. So what we are doing is we are measuring the distance between these two sets by the measure of the symmetric difference, but localized inside the region of finite measure. So we are measuring the size of this set and declare that this is the distance between A and B. And what you can easily check is that this collection of pseudometrics makes our Boolean ring into a topological ring, which means that every Boolean operation, say union, intersection, symmetric difference, relative complements, they are all continuous with respect to these pseudometrics. All right, so by the definition, it is obvious that this topology is not able to distinguish elements if they are not distinguishable in the perspectives of regions of finite measures. What I mean is that, for example, let's say our measure is either 0 or infinite on every element. In that case, the generated topology must be the indiscrete topology. Yeah, right? Because every t inside this set must has measured 0. Therefore, these pseudometrics are all identically 0. Therefore, the generated topology must be the trivial topology. Yeah, actually, more generally, the topology we define only depends on the semi-finite part of the measure. So we call a measure semi-finite if the measure of any element can be approximated by the measure of its localization inside a region of finite measure. And I think probably this definition is different from what you possibly remember. I think it would be something like this. Yeah. The thing is, these two definitions are in fact not equivalent, and this one is in fact strictly stronger condition. Yeah, they are actually equivalent if you assume further that your Boolean ring is sigma complete and your measure is countably additive, but they are in general not equivalent. And this one is really the right definition of semi-finiteness. Please allow me to rant a little bit here. I mean, I think there is a very weird tendency in the way measure theory is taught these days. I mean, they usually define things in the way that is easiest to check in practice, and then they show that their definition is equivalent to what they are really supposed to be. Yeah, which is horrible. I think this one is one example. They define it this way, and then they show that they are equivalent. Yeah, which is horrible. And another example is absolute continuity, which is usually defined in terms of null sets. But yeah, really, that's not the correct definition as far as I can tell. Anyway, end of the rant. So for any measure mu, we can define the semi-finite part of it with this obvious-looking definition, and one can show that this is indeed a semi-finite measure. And you can see that, for example, if our measure is either 0 or infinite on every element, then the semi-finite part is identically 0. Right, so and here's a proposition which says that our measure is not distinguishable from its semi-finite part in terms of the topology they generate. So from now on, we'll always assume that our measure is semi-finite, because otherwise we can just take the semi-finite part. Yeah, great. So here is an interesting result, which says that a semi-finite measured ring is complete Hausdorff topological ring if and only if these two conditions hold. The first one is that our Boolean ring must be complete as a Boolean ring. And second one is that our measure is strictly positive and order continuous. So being complete as a topological ring means that every Cauchy net converges. Being strictly positive means that the only element having the zero measure is 0. And being ordered continuous means that for any increasing net inside a Boolean ring, that admitting such that it admits the supremum inside the Boolean ring. So we're assuming that the supremum exists. Then the measure of the supremum is precisely the limit of the measures of A alphas. So note that if you replace this word net by the word sequence, then this is precisely what's called continuity from below. You might have learned from that measure theory. And continuity from below is known to be equivalent to countable additivity, right? So yeah, so ordered continuity is a far more stronger condition than sigma additivity, because nets are far more general than sequences. Yeah. By the way, sigma additivity is a synonym for countable additivity. Yeah.
Junekey, I have a question.
Yeah. So it's.
Can you remind me, is a complete Boolean ring, is that every subcollection has a supremum?
Right.
Okay, cool. That's what I thought. Yeah. Thank you.
Great. Yeah, so I will not get into the proof of this theorem, of course, but let me just briefly mention this. So it can be easily seen that by just expanding the definition, you can see that every increasing net must be Cauchy with respect to the topology we have talked about. Therefore, if we assume that our ring is complete and Hausdorff, this Cauchy net must admit the unique limit. And because of the continuity of Boolean operations, one can show that this unique limit must be the supremum. So this is how you show that your Boolean ring is complete if you assume this. And things like ordered continuity follows from topological continuity of this measure with respect to the topology it generates. So that's how you see only if part. And the if part is relatively more non-trivial. But yeah, it's sort of delicate, but yeah. Anyway, I'll not get into that. And so what I want to emphasize here is that the topology we defined quite well captures the essence of the measure theoretic properties of the measure, so that being measure theoretically nice, as written here, is equivalent to being topologically nice, as written here. So yeah, those two are really the same thing. All right, so let's note that every topological ring can be naturally densely embedded inside a complete Hausdorff topological ring, which is called a completion. So thanks to the previous theorem, we can expect that any measured ring can be naturally embedded inside a nice measured ring just by taking the completion. And this is indeed true. So for a semi-finite measured ring, we can uniquely extend our measure onto the completion so that the topology generated by this extended measure is precisely the topology as the completion of B. Therefore, in particular, the topology generated by this extended measure must be complete and Hausdorff. Therefore, by the previous theorem, the completion must be complete as a Boolean ring. And also the extended measure must be strictly positive and order continuous.
Just a question. Is it obvious that this completion must be a Boolean ring?
Yeah, it's not really hard to show, but yeah, maybe it needs proof anyway.
Okay, yeah.
Yeah. Okay, so I will not get into the proof, and really the lesson of the theorem is this: we don't care how bad our measured rings are because we can just complete it, and the result is always a very good measured ring, order continuous, strictly positive, complete as a Boolean ring, something like that. So all we need to do is really just to translate statements about the original measured ring into the statements about the completion and vice versa.
Okay, I'm gonna ask an insanely vague question that at the end of the talk, if you don't understand what I say now, at the end of the talk, I'll make it really precise. Do you leave measure theory if you do this completion procedure? In the sense that if I start with a measure and I do this Boolean completion procedure, do I leave classical measure theory?
Of course.
Cool.
Yeah.
All right.
That's why, yeah, I mean, this is the reason why we are doing this.
Yeah, I figured. Okay.
Yeah.
Nice.
So, yeah, this is why I didn't bother to impose sigma completeness or sigma additivity when we define measured ring. And also, yeah, this is one of the merits we gain from this abstract viewpoint. So yeah, using this kind of technique, for example, we can show something like this. So let's say, for example, the Radon-Nikodym theorem for finitely additive measures, which is not so straightforward to do in the orthodox pointed measure theory. Anyway, yeah. So yeah, and I just want to mention this. So we can do something similar with locally convex space valued measures. But yeah, it's kind of more complicated to do so. So I'll not get into that anyway. All right, so let me explain how these are relevant to the conventional measure theory. So let's think of measure space in the conventional sense, so that we're assuming that this is a sigma algebra and this is a countable additive measure. And think of the set of all null sets, and we call it the kernel of mu. Then it's an ideal because it's obviously closed under finite joins or finite unions. I mean, it's even closed under countable unions, right? So and then also it's downward closed because of the monotonicity of the measure. So it's an ideal. And since we have a ring and an ideal, we can think of the quotient ring, right? And what we are quotienting out are precisely the sets that have no measure. Therefore, we can define the induced measure on this quotient ring. More concretely, for each equivalence class that we can find from this ring, just take any representative and assign the measure of that representative to the equivalence class. Then it's not hard to show that this assignment really does not depend on the choice of the representative. So that's how you define this function, and you can show that this is a measure. This is indeed a strictly positive measure, right? Also, because of the sigma completeness of this ring and countable additivity of this measure, those properties continue to hold for this quotient ring and this induced measure. But in fact, we can say further. So given that our measure is finite, this quotient ring is in fact complete, not just sigma complete. And this measure is order continuous, not just countably additive. Yeah. The core reason behind this is that we have the so-called countable chain condition, CCC in short, for the quotient ring, which basically follows from the finiteness of the measure and strict positiveness of the measure. And this CCC really allows us to upgrade our sigma completeness into completeness and sigma additivity into order continuity. yeah, details will be omitted. Yeah, in fact, I was pretty shocked when I first saw this proposition. I mean, it's pretty amazing that just by getting rid of null sets, we no longer need to care about countability anymore. So yeah, note that the price we paid here is that our Boolean ring is no longer a set algebra of our pointed space. So I guess this was the primary reason for me to look into the point-free measure theory. Yeah. Anyway.
I'd just like to point out one consequence of this is that the monotone convergence theorem holds for nets if you interpret the limit correctly in the finite measure setting. So that's just like to highlight what Junekey is saying. That is insane.
Yeah, that's right. Yeah.
And also, just to perhaps say this for myself. So basically what's going on here is that instead of using like the sets from classical measure theory, we're now using like sets up to like measure 0 are objects, more or less. Like,
yeah, so so the measurable set here is not really a set. It's an equivalence class of sets.
Okay.
Yeah.
If you don't want to leave that realm, though, you just replace the containment relation with the essential containment relation, which is contained in up to measure 0. So, yeah.
All right, so the next topic is the theory of measurable functions. Analysis is all about functions, right? So if we can't talk about measurable functions, then there is no point of doing this, right? I mean, yeah, of course, this entire talk is pointless, though. But luckily, still we can define measurable functions, even though it's quite pointless to do so. Yeah. So the first step is to define simple functions in an algebraic manner. So just think of the free R vector space over the Boolean ring. And we take the quotient by some obvious relations. More precisely, the free basis vector corresponding to an element inside a Boolean ring is supposed to be the indicator function on that measurable set. So given this interpretation, we can derive necessary relations that these free basis vectors must satisfy. And we take the quotient by those relations, then what you get is the algebra of simple functions. So the point here is, of course we don't have points, but the notion of points plays no really crucial role here. When we are talking about simple functions, they can be just defined without the notion of points. So after defining simple functions in this algebraic way, we can abstractly define various function spaces. For example, recall that in pointed measure theory, bounded measurable functions are precisely the functions that can be written as uniform limits of simple functions. So we can define point-free bounded measurable functions as elements inside the completion of simple functions with respect to the uniform norm. Yeah, also we can define things like integrals of simple functions. Yeah, just like we did for pointed simple functions, there's no difference. So we can talk about things like LP spaces or p-integrable functions, things like that. So yeah, there are ways to define point-free measurable functions in this way, but the problem of this pointless definition of measurable function is that it's too pointless. I mean, yeah, to be more precise, I mean, for example, it's not apparent how to talk about things like functions that are both L1 and L2, for example. I mean, there are ways to do things like that in this setting, but it's not so apparent. Also, note that it's very common in measure theory that we first construct a measurable function and then show that it's p-integrable. But it's not clear how we can mimic such a procedure in this setting. So my goal today is to introduce a better way of defining point-free measurable functions which is to use the so-called stone duality to recover the notion of points. But this time, the points will be better points. So yeah. So recall that a topological space is totally disconnected if every component is a singleton set. And we call a compact Hausdorff totally disconnected space a stone space. Yeah, so here's a very famous duality theorem by Stone, which says that the category of Boolean rings is contravariantly equivalent to the category of stone spaces. And those two categories are linked via these two functors, spec and Klopen. So the first one, spec, which spec takes a Boolean ring and spits out the space of prime ideals endowed with the so-called Zariski topology. And this functor Klopen takes a stone space and spits out the set algebra of Klopen subsets of the stone space. Yeah, that Zariski topology. I mean, yeah, the Zariski topology being Hausdorff already sounds ridiculous, but it is indeed not only Hausdorff, but even totally disconnected in this case. So yeah, it's quite amazing. I'll not get into the proof, although it's quite simple. But the thing to remember here is that any Boolean ring can be viewed as the algebra of Klopen sets of some stone space that is called the spectrum of the Boolean ring. So this is what really this theorem is telling us. Right. So here is the thing. So it can be shown that the algebraically defined point-free simple functions are in fact equivalent to Klopen simple functions in the spectrum. So what I mean by Klopen simple function is just linear combinations of indicator functions on Klopen sets. And, you know, indicator function on the Klopen set must be a continuous function. So linear combination is also continuous. And yeah, because our space is totally disconnected, Klopen sets forms a base for the topology. And our space is Hausdorff. Thus, Klopen simple functions actually separate points inside the spectrum. So we can apply the Stone-Weierstrass theorem to conclude that simple functions form a uniformly dense subspace inside a space of continuous functions on the spectrum. Right? So the notion of bounded measurable functions, which we define as elements in the uniform completion of the space of algebraic simple functions, is in fact equivalent to the notion of continuous functions on the spectrum. They're the same thing. Yeah, which is nice.
Is it possible to describe directly or in a reasonable way a measure theoretic example of the spectrum?
I'll say it's beyond our imagination.
I was about to say it's probably not constructible in some way.
Yeah.
Okay, cool. Great.
Okay, so now think of the conventional pointed situation. Here, we still have the space of bounded measurable functions are equivalent to the space of continuous functions on the spectrum, because both of these spaces are just the completion of the space of simple functions with respect to the uniform norm. And think of the operation of taking the quotient by almost everywhere equivalence, and which can be written as this arrow. So we are taking the quotient by almost everywhere equivalence, so that we are going from this space into onto L infinity. And one can show that this operation is actually equivalent to taking the restriction onto the spectrum of this quotient ring, which can be shown to be a compact subset of the spectrum of the set algebra. And this restriction map is surjective because of the Tietz extension theorem. So we can conclude that this L infinity space is in fact naturally isomorphic to the space of continuous functions on the spectrum, but in this case, not the set algebra, rather the quotient ring. Yeah. So even the space of equivalence classes can be identified to a space of continuous functions, which is very nice. Yeah. So in pointed measure theory, the so-called Littlewood's principle says that measurable functions are almost continuous functions, but in point-free measure theory, they are literally continuous functions. Yeah, we just need to replace our space by some weird topological space. And I think this is really nice because we can enjoy lots of goodies of continuous functions like meaningful pointwise values. But at the same time, we have enough flexibility offered by measurable functions thanks to the fine enough topology of the spectrum. Yeah, so I think I said enough for bounded functions. So let's talk about unbounded functions for a while. Okay, so let's think of a finite measured ring which has a complete and Hausdorff topology. And here, finiteness is really there just to liberate myself from explaining uninteresting technical details. But in fact, you can replace it by semi-finiteness. It's really sufficient. Now, for each dense open subset of the spectrum, consider the space Cu, R, the space of continuous functions on this dense open set. And note that this open set is not necessarily compact. So yeah, functions in this space may not be bounded. They can be unbounded. And we endow this space with the topology, compact open topology, or equivalently the topology of uniform convergence on compact sets. And for given V and U, both are dense open subsets of the spectrum, we can think of the restriction map from Cu into Cv. And this is a continuous injection. The reason why it is an injection is that V is dense. And so as we shrink U, we get a directed system of topological vector spaces with restriction maps. So why not think of the direct limit? So we call this direct limit L0 and call each element in this direct limit as possibly unbounded, point-free measurable functions. So yeah, how dare we call these elements measurable functions, right? So it looks quite non-intuitive. But here is a fact. So in the conventional pointed setting, the space of all real-valued measurable functions, bounded or unbounded, can be shown to be the completion of the space of simple functions with respect to the topology of convergence in measure. Yeah, this is a known fact. Hence, we show that the same is, if we are able to show the same thing is true for this direct limit, then it is justified to call our elements as measurable functions, right? So, and it's indeed true. Yeah, so this theorem tells us that unbounded measurable functions are still just continuous functions on the spectrum, just like bounded ones. And the only difference is that they may not be defined everywhere, just defined on a dense open set, which I think is a very satisfactory result, right? They're still continuous functions. But I still don't have a definite answer for this question. Is there a similar result for locally convex space-valued functions, for example? To be more precise, this direct limit will certainly not the completion. But I don't. It doesn't matter because expecting completeness is very often too much if we go beyond the realm of metrizable spaces. So more reasonable question might be something like, is the topology on this direct limit coincides with the topology of a convergence in measure, something like that. And I suspect that the answer is no in general, if you're working with non-metrizable spaces. But I still think this direct limit construction should be the right way of defining measurable functions, even for that cases. But anyway, I'm not sure, yeah. And another interesting conjecture is that whether this L0 is the sheafification of the functor L at infinity. Yeah, I mean, yeah. So what I'm talking about is this. So any pole set is a category in its own. So in particular, a Boolean ring is a category. And we can view L infinity as a functor or pre-sheaf on this category, which assigns the space of bounded measurable functions on each element of the Boolean ring. And since our Boolean ring is complete, we can actually endow this category with so-called Grothendieck topology, which is a generalization of the concept of topology. And we can think of the sheafification of this pre-sheaf L infinity with respect to that Grothendieck topology. And it seems to me that it is very reasonable to expect that what we get should be L0 as defined here. But yeah, I'm not really familiar with this abstract nonsense, so I currently have no idea how to show this. But once it turns out to be true, I guess this gives us yet another justification of the claim that this is really the right way of defining measurable functions, even for vector valued cases. Yeah. So yeah, what I'm thinking is that this is the reason why vector valued measure theory sucks. I mean, yeah, in the pointed setting, because the notion of measurable functions in that case is not really. I mean, it's different from what really it is supposed to be. So yeah, that's my hypothesis. I don't know the answer, but yeah. Anyway, so yeah, let me finish after mentioning some consequences that we can draw from this theory without proofs, of course. So the firstly, every LP space can be embedded in this L0 because the convergence in measure is weaker than any of the LP convergences. So we can naturally talk about things like functions that are simultaneously L1 and L2 or something like that. And also we get that every measurable function is locally a uniform limit of simple functions, which is sometimes pretty nice. Nice to know. And also with the definition of L0, we can show, yeah, convergence theorems like monotone convergence theorem in this point-free setting, but for nets, yeah, not necessarily sequences. So yeah, this is all I prepared, and thank you for listening. Yeah.
All right, let's thank the speaker. Are there any questions before I start asking questions?
Yeah, so I was wondering if this has any like connection at all with distributions. So I know those are like kind of annoying to define like pointwise. Like you want it to be like infinite at 0.0 and like 0 everywhere else. Like, does this fit into that framework at all?
I think the theory of distribution is very closely tied with the notion of derivative. But the notion of derivative inherently requires us to think of points. So I think it will require us to, I mean, if I want to point-free, I mean, make a point-free theory of distributions, maybe I think I should do a lot of more works. I don't know. Yeah.
Yeah, fair enough.
Anyone else?
So it looks like you were using like spec of your Boolean ring as a topological space to do a lot.
Right.
Do you know if viewing it as a scheme is like a useful perspective in this? Or
Theory of schemes?
yeah, so if you view like spec of your Boolean ring as a scheme, namely it seemed like all this stuff in the presentation was pretty schemy. Like L0 looked like it was like taking a stock, and you had that one commutative diagram with L infinity.
Yeah, something like that. I mean, yeah, I always love to learn algebra, so I'm pretty eager to apply the theory from algebra to analysis. But yeah, honestly, I'm not really I don't know much of algebraic geometry. So
Okay, that's fine. I just
yeah, what I remember is I defined Boolean rings as rings with unity, right? But actually, it does make sense to think of Boolean rings without unity. And in that case, we can still define spec. But in that case, the spec becomes a locally compact stone space, not compact stone spaces. And we can show that a locally compact stone space is in fact a scheme in the standard scheme theoretic sense. Yeah. Because we can cover it by clopin sets, compact open sets. Each of them is really the spectrum of some Boolean ring. So yeah, what I know is something like that, but not so much about, I don't know much about algebraic geometry, so maybe I'm not really qualified to answer that question, I think.
Yeah, no worries. Thank you.
Anything else? Okay, I have a question. So you said you wanted to liberate yourself from technical details. I will now reshackle you to those details.
Okay.
What do you get, or what should you get as L0 in the semi-finite case?
Same thing. So there's no difference. Yeah.
Okay, that seems like a
The
problem.
the only difference is on the proof. Yeah, so the result doesn't really change.
So if it feels like it should be, maybe I have to think about this a little more. It feels like it maybe should be measurable functions that are bounded off a set of measure 0. Bounded off a set of finite measure.
Okay.
So there's a construction in von Neumann algebras called the set of affiliated and tau measurable operators.
Okay.
And I would have to sit down and actually think about this, but I think what you traced for L0 seems to be more the route you would take to define tau measurable operators. And in the commutative case, tau measurable is really measurable functions that are bounded off of a set of finite measure. So I'm not sure which part I'm not following correctly, but that's very interesting. If you actually get back all of L0, that would be surprising.
Yeah, I suspect that what you're saying really makes sense. I think maybe that's true. I guess, this theorem is, as far as I know, my original result, but I think it is totally possible that it has been known for a while. But yeah.
Oh, no, I'm not claiming that. I'm just, kind of getting intuition for the construction, because it seems to lead to something different than it actually does. Did you write this up anywhere?
Right, what?
Did you write this down anywhere?
Actually, no. Yeah.
Okay, if you ever do, I'd be interested.
Well, yeah, if you want to talk more, maybe we can set a private meeting.
Yeah, that's probably appropriate. Are there any other questions? All right, let us thank the speaker once more.
Thank you.